Welcome to the video on Chapter 3, Section 1, Tangent Lines and Rates of Change. Now, in this video specifically, we are just going to talk about these tangent lines here, and we'll get to rate of change a little later. Now, Chapter 3, what it does is it gets into the beginning of answering that very first question of calculus. And if you remember from the first day of class, it talked about calculus tries to answer two basic questions, and that is, one, finding an instantaneous rate of change, and two, finding the area of odd shapes. And so Chapter 3 starts answering that first question. Now, before we get into that, I want to talk a little bit about what you remember from geometry about secant and tangent lines. Now, some of you may remember a lot, and you can tell me exactly what the definition is. Some of you may not even remember those words at all. So we're going to give a quick synopsis of what they are so we can move into the calculus version of secant and tangent lines. Now, in geometry, you had a secant line that was, typically we talked about circles when we use secant and tangent lines, but a secant line was joining 2 points on a circle, and any 2 points. Now, in order to do that, you would have to go through the inside of the circle at some point, and this line could continue on past those 2 points, but the main definition of a secant line is just to join 2 points of a circle, whereas a tangent line is a line that only intersects 1 point of a circle. Okay, now we're going to deal with these same definitions, these same working definitions of secant and tangent lines. However, we're going to look at them with functions and curves, and it deals the same premise here. Okay, so let's take a look here first at a secant line. Now, this is just a basic parabola here, and we have this black secant line here that joins 2 points. The first point is at x0, f of x0, okay? This is just the x value, just some x value, doesn't matter what it is, and we know it has a y value that when you plug that x value into the function. And then there's another point up here later on in the curve that we're going to call x1, okay? And that has its own corresponding y value of f of x1. Now, we know how to calculate the slope of this line. Using our Algebra 1 skills, we simply just find the change in the y over the change in the x. Okay, in this case would be the f1 minus f0 all over x1 minus x0. And we can calculate the slope of that secant line. And so we need to be able to do that. We need to be able to calculate the slope of any secant line in any function, and that's simply just two x values. We want the difference between those two x values in the denominator and the difference between their corresponding y values in the numerator. Now, the goal of this is to use this slope calculation that we already know how to do to find the slope of a tangent line. All right, and in order to do that, we need to look at a little simulation here. So this is another simple parabola. It's not necessarily the same one, but the key is we have a point over here, a green point on the right and a red point on the left. Okay, now if we connect those 2 points with this green line here, that is a secant line because it's intersecting a curve at 2 points. Whereas this red line is a tangent line because it's only intersecting the curve at 1 point. And if you notice, I can move the red dot around and it changes the slope of the secant line and it changes the slope of the tangent line as well. Alright, now what I want you to see here is if as we move these 2 points closer and closer together, if we get them closer and closer and closer, what's happening with the tangent line? Well, the tangent line is starting to become the secant line. I can come from either direction, and once those 2 points are overlapping, the tangent line has now become the secant line. Okay, so what does that tell us? That tells us that as x0 becomes closer and closer to x1, this slope of the secant line becomes the slope of the tangent line. So we can define the slope of the tangent line with a limit. As x0 approaches x1, this expression for the slope of the secant line becomes the slope of the tangent line. And this is big. This is something brand new. This is something that we've not been able to do in your math career. finding a slope of a given point, the slope of a curve at a given point. Now, this limit right here is okay, it's workable, but we're going to try to clean it up a little bit, and we're going to make it look a little nicer by simplifying a few variables here. First, what we're going to do is we're going to say that this distance between x0 and x1, we're just going to call that h. All right? And so if we do that, then we can simply say that, well, this difference between x1 and x0 is simply h, and we can define x1 as x0 plus h, and this is where we an expression for the slope of a tangent line defined by a limit. So this is pretty significant here. All right? And what this allows us to do is let's say hypothetically we have a function, let's say f of x is equal to x squared. And I want to know, well, at the point 3, 9, which by the way, this point is in the function f of x equals x squared because 3 squared is 9. At that point, what is the slope of the tangent line? And so if I want to find what is the slope of that line, I can plug it into this limit and say that my slope of the tangent line is equal to the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. Now, what we have to do is we have to treat 3 plus h as our variable that we're plugging into f. And when we do that, we have to square the entire binomial of 3 plus h. And so what that gives us is it gives us the limit as h approaches 0. We have to use a little binomial expansion here to say that it's 9 plus 6h plus h squared minus f of 3. We know when you put 3 into x squared, we simply just get 9. And all of that is still over h. Now, we can simplify things here. 9 minus 9, those go away. And then the h cancels with the h with the 6 and gets rid of one of those h's. So we're left with the limit as h approaches 0 of 6 plus h. Well, if h is going to 0, then that's going to 0, and we're left with 6. So what does this number tell us? This number tells us that the slope of the tangent line at the point 3, 9 of the function f of x equals x squared is 6. Now, with that information, given a point in the slope, we could use our Algebra 1 skills to write an equation of that line. We're not going to do that right here, but that is something that could be asked of you and something that you should be able to do. This is your slope. This is the slope of the tangent line, and we have the point that it goes through. All right, well, even better than that, this can give us one other thing. We can think about, well, now let's just think about an arbitrary point. So let's deal with the same function and say we have f of x equals x squared. But let's not just pick a point of 3 or a point of 2. Let's pick a point of x. And, well, what's its y value going to be? Well, it's just going to be f of x. All right? So let's pick that point and let's plug it into our limit here. So this says that the slope of our tangent line. Now let's pause for a second and figure out why would we want to do this. Well, why are we doing this? This will give us a function. At the end, this will give us a function that will tell us the slope of any point along this original function of f. So it will actually get a slope function. All right, we're going to define that in a moment. So let's take a look at this. If we plug in x into this expression here, then we get the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so we plug in x plus h into our function f of x equals x squared. So the same thing, we're going to have to expand that binomial. And so we still get the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared. Now why is it just minus x squared? Because f of x is equal to x squared. And that's all over h. Now notice, x squared cancels with x squared. H cancels with an h. So what are we left with? We're left with the limit as h approaches 0 of 2x plus h. Now if h is approaching 0, then this term is approaching 0, and we're left with 2x. So what does this tell us? This tells us that we can pick any x value we want, and we can know the slope of that x value, the slope of the function, slope of the original function at that x value simply by multiplying by 2. Okay, and this function, this special slope function as I referred to it earlier, we give a name, and we give that name f prime. Okay, notice the little apostrophe here. We call that f prime of x, meaning the slope function of x. If we have some function f, we can write a function that describes the slope of that function in terms of x. And how do we write that function? We write that function by evaluating the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Okay, well that concludes the first piece of section 1 of chapter 3. Now what I want you to do is in your book, on page 170 and 171, I want you to look at two different problems, number 2 and number 4. Okay, I'm going to post another video that helps you set up these two problems, and actually I'll work one of the problems from start to finish. That will be on the website as well as this video. But before you come into class tomorrow, I need you to try those two problems and give them a shot. If you need some help, check out the second video to get you started on the right path.